Hello and welcome to Lecture 3 of Vectors, and now we're going to connect the ideas we've been looking at with motion diagrams with what we've just learned about vectors. So here's a simple motion diagram, although it's not a one-dimensional motion diagram like most of them we've been looking at, right? This object is moving in a curved path. And let's first talk about how we define position and displacement vectors. So a position vector tells you how to find the location from the origin of the coordinate system. So the position vectors for points 2 and 3 would be drawn this way. They point from the origin to the location that you're talking about. A displacement vector points from the starting point during the time period it's talking about to the end point. So the displacement vector for the time from 2 to 3 would be this vector here. And we'll see in a moment that these are related in exactly the way we've talked about, that that delta x32 is going to be x3 minus x2. But now I just have to point something out that's a detail. I said before that vectors are independent of how you choose your axes. Now, technically that's not quite true. They're independent of the orientation of your axes. But most vectors are also independent of where you put your origin. However, a few of them aren't, and position vectors are one. So just notice, because position vectors are defined as pointing from the origin to the point, that if you move your coordinate system, your position vectors change. But notice that the displacement vector hasn't. It truly is independent of your choice of axes. So let's just see graphically how this works out with getting a displacement vector. We know that displacement is defined as a change in position, so it's a final minus initial. So let's say we have some final position here, x2, and some initial x1, and so by definition our displacement is x2 minus x1. And let's see what delta x21 looks like. Let's carry out that vector subtraction. So I'm going to grab a copy of x2 and throw it over here. And I'm going to grab this copy of x1, and now I'm going to flip it around, which means I have to flip it both horizontally and vertically. And so there we go. And so if I put them head to tail, like so, now I'm going to get delta x looking like this. Let me just change its color so it's clear which one it is. So there is delta x. And I'll just slide it over, and here you see it is, as we thought, the vector which points from the initial location to the final location. So remember that the way we get an average velocity is by the displacement over the time interval that that displacement takes place in. Only before we didn't have vector symbols on this. And so these are just reminding us that now we have to pay attention to the vector nature of these, whereas before plus and minus was enough to keep track of all the direction information we needed to. But that's not going to be good enough anymore. Now the other thing I'm going to do is this tells us we're working entirely in terms of displacements. And so we don't care about the positions, and displacements are independent of our coordinates, so we can get rid of all that. Now, how are we going to go about doing that? We want to take this displacement and get a velocity from it. So we'll get this velocity v32, and maybe I should write v_av32, but there is such a thing as too many subscripts. And you may be looking at this and saying, what? How do I do that division? I don't know how to divide a vector by a scalar, but actually you do, because you could rewrite it this way, and now this 1 over delta t is a scalar, and we're multiplying a vector by a scalar. And we know how to do that. It's just going to rescale the vector. So we're going to get a new vector that's in the same direction as delta x32, but a different length. Well, what length? Suppose that the length of this delta x32 is 2 meters. And let's just say that delta t is 0.2 seconds, right? These numbers are just a sequence of numbers, not actual times. So then how long is v32? Well, if you just do the division, you might say, oh, well, it's 10 meters per second. But saying that the vector is 10 meters per second long is just like me saying a few lectures ago that my age is 43 kilometers. Right? Meters per second aren't a unit of length, but our scale in the diagram is in meters. Well, what that means is that we can actually draw our velocity vectors any length we want, because they're not to scale on the diagram. And so we just have to be consistent. And so let's just take the convention that we'll always draw an average velocity vector the same length as the displacement vector that it's replacing. So now we can just replace all those displacement vectors with velocity vectors. And if you look back at lecture 5 of the one-dimensional motion unit, you'll see that I've already done that. So what we need to do now is learn how to add acceleration vectors to a general motion diagram that's all curvy with speed changes everywhere. And this, in fact, is the whole point of what we've been doing. We want to be able to figure out acceleration directions no matter what kind of motion we're talking about. So I've been careful in this motion diagram to sort of include everything, including the kitchen sink. So there's a part here which is speeding up in a straight line. And there's a part over here where this object is slowing down while moving in a straight line. There's a part here where it's going around a corner at constant speed. There's a part up here where it's going around a corner while slowing down. And there's a part up here where it's going around a corner while speeding up. So that's all the possibilities. And we are going to use the way we've been working with acceleration. It's a change in velocity over a change in time. And remember, this is a change in velocity. I see students all the time get mixed up between change in velocity and an average velocity. Here, this is a final velocity minus an initial. And so if we were to find an average acceleration at some point, we need two velocities, an initial and a final. So we can choose this as our initial and this is our final, right? One before and one after the point we're interested in. And remember, we talked about how this is an average velocity over this whole time interval, but that makes it a good estimate of the average of the instantaneous velocity here in the middle. And similarly, this velocity here, this average velocity, is a good estimate of the instantaneous velocity here. And so now we can find a delta v, or an approximate delta v, from this point to get an average acceleration over that time interval. Okay, I've just taken a moment to clean up the diagram a bit, and now I'm going to find the acceleration here. So I need, for a delta v, I need a vf and a vi. So here's my vf. I'm going to copy it out here. So it's about like that. So there's my vf. Here's my vi, but remember, I have to flip it because I need to subtract it from vf. So I'm now going to add that in, so it's about like this. And so my delta v points like this. And we already know what this division by delta t does. All it does is rescale that, but these are already in dimensions where their scale on the diagram is meaningless, so we can draw this any length we want. So I'm just going to draw it in there. Now notice it points towards the middle of the circle that this is going around. Okay, and you may have encountered that in another physics course, that when something is going around in a circle, the acceleration is into the center. Now, technically, that's only when it's at constant speed, as we'll see, and we've seen it now from a motion diagram and vector subtraction. Okay, now I'm going to do this part where it's turning while slowing down. So once again, I need a VF and a VI. So I'm going to copy my VF out here. And I need my negative VI, which looks like this. So I'm going to copy it over. It's roughly like that. And let me label those. So this is my VF. This is my minus VI. And so now I have a delta V right here. Delta V. Okay? And so, just make some room there. So look, I'm going to draw that in, and it points inward, but it also points back. So you can think of this as that the part of this vector that's pointing inward is what's causing the curve in the path. And the part that's pointing back is what's causing the slowdown. So you can probably guess then what's going to happen over here where it's speeding up and turning. But let's see it. So I'm going to copy my VF, which is about like this. And I'm going to copy my negative VI, which is going to point this way. And so here's my delta V. And I'll just copy it in. And you see that it is also not straight to the center of the circle. It's to the center and forward, right? And so again, the part that's pointing in causes the curve. The part that's pointing forward causes the speeding up. Okay, I just cleaned up the diagram again, and let's finish up. So let me do this speeding up part down here. And we know how this has to turn out. We already know that the acceleration vector has to point forward, but we haven't seen it from vector subtraction. So let me quickly do that. Here is our VF. It points forward like so. And I will subtract VI, so it points back like this. And so my delta V is like so, just like we thought, right? So, and now, once you've seen this, you don't have to go through this whole laborious process of the vector subtractions every time. I can tell this is speeding up going in a straight line, so it points forward. This is going around in a curve at constant speed, and so these point straight into the center. This is going around a corner and slowing down, so it points inward and back. And same here. And these look like they're constant velocity. But then here we're going around in a corner and speeding up, so it points forward and in. Same here. This is another constant velocity. And then here, if you do the same thing as I did over here, you'll see that this works out just the way we know it should, that when it's slowing down going in a straight line, the acceleration should point back. And there we go, our fully done motion diagram with acceleration vectors on it.